Hello, my name is Greg Rao, lead member of the Planet Physicians. Dire climate and environmental circumstances are now rapidly unfolding due to our growing fossil fuel use and resulting CO2 emissions trajectory. It is therefore time for some radical new thinking as to how to sustainably satisfy our energy demand while also stabilizing, if not reducing, atmospheric CO2. As I will review, our technology simultaneously addresses both of these issues by employing a novel electrogeochemistry process. The basis of our approach is well-known saline water electrolysis, but where we encase the anode in a porous mass of base mineral like calcium or magnesium carbonate or silicate. This consumes and neutralizes the acid normally formed at the anode, thus forcing the accumulation of the hydroxide that is normally produced at the cathode. The resulting hydroxide-enriched solution then readily reacts with and consumes atmospheric CO2, forming dissolved bicarbonate. When powered by non-fossil electricity, the system would then provide a way of generating carbon-negative hydrogen. Proof that this concept works is seen in dramatic increases in electrolyte pH in the presence of base minerals, and in observing that this pH increase is subsequently lowered via solution aeration and reaction with atmospheric CO2. In turn, very significant increases in dissolved bicarbonate are seen in the electrolyte relative to that in experiments where minerals are absent. The preceding proves that we can electrolyze common salt solutions in the presence of common rock minerals to make those solutions strongly absorptive of air CO2 while also producing hydrogen and bicarbonate. Siting such systems in, on, or around the ocean could make use of the massive supply of renewable energy, minerals, salt water, and CO2 absorption area associated with 70% of the Earth's surface. The abundance of these resources implies that our process could be done at very significant scales. Also, the generation of ocean alkalinity by such systems could be helpful in chemically offsetting the effects of ocean acidification that is otherwise consuming carbonate alkalinity and thus impacting shell-forming organisms. While it is very difficult to extrapolate the economics of such systems from our initial lab experiments, we estimate a cost of about $100 per ton CO2 mitigated. This is some 6 times lower than the cost for direct air capture recently estimated by the American Physical Society. What is now needed is further research to determine the optimum designs, operating procedures, siting, economics, and net environmental benefit of such systems. The societal, regulatory, and geopolitical implications also need to be understood. We ask for your support in this effort.